if we have three hoops, concentric, that means they all are centered at the same point. Three concentric hoops, 1, 2, 3. The radius of the inner hoop is 0.4 meters. The next is 0.8 meters. The next is a radius of 1.2 meters. The inner hoop has radius, a mass of 2 kilograms, then 4, then 6 kilograms. If we have three such hoops, then what's the total moment of inertia? This is the quiz problem for today. Well, the moment of inertia is what we get when we add up the mr squareds. And what's the mr squared for the first hoop? Well, all the masses, all the point masses, remember when we add up the mr squareds, we've got to add up all the point masses at their own respective radii. Okay? All the masses here happen to be at the 0.4 meter radius. And all the masses of the second hoop happen to be at the 0.8 meter and the third at the 1.2 meter. Now that's an ideal hoop. Everything is right at the same distance. Okay? So if we add up all the sum of the mr squareds, in this case it turns out to be fairly simple. We just do mr squared for each hoop because all the r's are the same over each of the individual hoops. So that on the first hoop all the r's are 0.4 meters and the mr squared, if we add up all the mr squareds in the first hoop, we get 2 kilograms times the square of 0.4 meters. 4 kilograms times the square of 0.8 meters, 6 kilograms times the square of 1.2 meters for the second and third hoops. And of course we can calculate these very easily and add them up, and we see that the total moment of inertia is 11.5 kilogram meters squared. Now the next part of the problem said, well, okay, let's apply a force of 8 newtons at the rim of the first hoop. And let's apply that force in the most advantageous direction for accelerating these hoops, and then let's figure out what the acceleration of the system is going to be when we apply that force. Okay, again, we assume that these hoops are rotating, constrained to rotate about some axle or something with so implicitly no friction. So how do we determine? We know the moment of inertia. How are we going to determine the angular acceleration of this system? Well, Newton's second law tells us that the product of the torque and the acceleration, that the torque is the product of the moment of inertia and the acceleration, which is just like F equals ma. Instead of force we have torque, instead of a acceleration we have alpha acceleration, and instead of mass we have moment of inertia. We calculate the torque of this force. It's 8 newtons applied at the 0.4 meter distance in the most advantageous direction, which is, incidentally, the direction that's tangent to the hoop, so that the force makes a right angle with the moment arm from the center of the hoop to the point of application. Okay, we get a torque then which we easily calculate to be 3.2 meter newtons, and from that we can easily calculate our angular acceleration by dividing torque by moment of inertia, and we go through the calculations. We end up with 0.28 radians per second squared.